Welcome to Maths with EJD. In this video, I'll be talking about the definiteness of a matrix, still under the subject of matrices. The definiteness of a matrix. All right, so our outline is like this. We'll have the introduction, then we'll talk about positive definiteness, semi-positive definiteness, negative definiteness, semi-negative definiteness, indefiniteness, and of course, we'll talk about the conclusion. So in the introduction, it is we know that in linear algebra, right? Matrices come under linear algebra in mathematics. And in linear algebra, matrices serve as a matrices serve as foundational tools with diverse applications in mathematics, diverse applications, as you can see already from the previous things we have been doing and some other things you're going to see later. So one critical aspect of matrix analysis revolves around understanding its definiteness. So you need to understand the definiteness of a matrix, which holds paramount importance in various mathematical contexts. In this presentation, we delve into the concept of matrix definiteness. Particularly, we explore the role of eigenvalues in characterizing the definiteness of matrices. Now, you can actually characterize the definiteness of matrices, using various parameters. In the future, probably I'll be talking about uh, quadratic form of a matrix, right? And there you can also see the concept of definiteness playing out, and that has some application in optimization and optimal control. Okay, but for in this case, we are basically characterizing the definiteness based on eigenvalues, since we've talked about eigenvalues previously. Okay, so talking about positive definiteness now, you should understand that a matrix A is positive definite. It is positive definite if all its eigenvalues are positive. So positive definite if all eigenvalues are positive. Okay. So for instance, look at this matrix A, 2 minus 1 minus 1, 2. Of course, you already know how to find eigenvalues, so I'm not wasting time with that. So the eigenvalues of this matrix are lambda 1 equals 3 and lambda 2 equals 1. And they are both positive. So because the eigenvalues are both positive, of course, for a 2 by 2 matrix, you expect to have two eigenvalues. And the two eigenvalues in this case are positive. If you have a 3 by 3 matrix, you expect to have three eigenvalues and so on and so forth. So all the eigenvalues are positive. So you can say that this matrix is positive definite. Now, what is the importance of positive definiteness? Matrices with all positive eigenvalues are often arise in optimization. They arise in optimization problems, and they have applications in statistics where they represent covariance matrices. Covariance matrices talking about how one factor varies with another. Covariance matrices ensuring positive definite property. So there are situations where you need to guarantee that the system is positive. Very important. And of course, there are situations where you need the eigenvalues to be negative, especially when you talk about stability, as you're going to see very soon. So then let's talk about semi-positive definiteness. So a matrix A is semi-positive definite. It is semi-positive definite if all its eigenvalues are non-negative. Now you'll see that uh, positive definiteness and semi-positive definiteness seem to look alike, but the issue is that for semi-positive for positive definiteness, right, you need the two eigenvalues to be strictly positive, not non-zero. But in the case of semi-positive definite, you just need the values to be non-negative, and non-negative includes zero. All right. So non-negative includes zero. So it's like positive definiteness is the strong case for semi-positive definiteness. So you need all your eigenvalues to be non-negative. So in this case, you have matrix A. Of course, because it is a triangular matrix, the eigenvalue is going to be 1 and 0 automatically, So the eigenvalues are 1 and 0, and they are both non-negative. So in this case, you see, the other time we're talking about the fact that the eigenvalues are positive, like strictly positive. But in this case, we are just concerned about them being non-negative. Non-negative means zero or positive, basically. But positive means you have positive numbers, not zero at all. So semi-positive definiteness includes cases where you have zero and then you have a positive value. So if you have a 4 by 4 matrix, right? And you have three of the eigenvalues as a uh positive natural numbers, and then one of them is zero, then you can still say that that matrix is semi-positive definite. So anytime you see the semi thing, or is it semi it is called, that's actually telling you that one of the eigenvalues is zero, in whatever case, whether for semi-positive definiteness or semi-negative definiteness. So in this case, the eigenvalues are lambda equals 1 and lambda equals 0, and both are non-negative. Now, there's a difference between positive and non-negative, right? So positive is actually non-negative, but what you say non-negative here because you are including zero, So what's the significance of semi-positive definiteness, right? Semi-positive definiteness is encountered in systems where non-negativity is a constraint. So like we don't want the system to be negative, such as physical systems or probability distributions. I work in an area of research, working with mathematical biology, right? Especially population dynamics. And it's possible that based on the structure of a model, you can actually get negative values for a population, and a population cannot be negative, right? So we need to put constraints of non-negativity. That is why you see parameters. So we can say that maybe parameter rho is greater than or equal to zero. This is to ensure positivity. Like this is to ensure that the parameter is not negative, because we cannot accept negativity in some circumstances. That is why so zero is still fine, right? It's possible a population can go extinct, so zero is fine, but a population cannot go negative. That is why we have to guarantee that positivity like that. So that's one usefulness of semi-positive definiteness. Okay, so let's see the next thing, which is about negative definiteness. Negative definiteness. A matrix A is negative definite if all its eigenvalues are negative, all its eigenvalues are strictly negative. Maybe I can put the word strictly negative. And strictly negative is to ensure that there is no zero as part of the eigenvalues. For instance, if you have this matrix A, which is -3, 1, 1, -3, the eigenvalues are -4 and -2, right? And they're both strictly negative. So you can say this matrix A is actually negative definite. So, and the significance of negative definiteness is such that negative definite matrices have applications in various fields, including numerical analysis, solving systems of linear equations, where they ensure stability and convergence properties. I talked about stability the other time. So when we do stability analysis of our dynamical systems, which I get to use a lot in my work as a modeler, doing mathematical biology and all of these things. So you need all the eigenvalues of whatever matrix you come up with from your model to be negative to ensure stability. Because if it's negative, it means that it is going to attain an equilibrium position. But if it's all positive, then the system gets to blow up, and then there's no convergence. So you see, though it's negative, right, but it has its own uses. Very important. Um, let's see. Semi-negative definiteness. You can already have an idea what this is going to look like going by what we had for semi-positive definiteness. So a matrix A is semi-negative definite if all its eigenvalues are non-positive. So you see the language has changed now. The other time we said they are all negative, but here we are just concerned about them being non-positive, meaning that zero is allowed and any negative values and zero. Zero is allowed. In short, I think that summarizes it. Consider the matrix A, which is -1, 0, 0, 0. Its eigenvalues are lambda 1, which is -1, and lambda 2, which is 0. And they are both non-positive. Non-positive. So zero is not positive. It's not negative, but the key is that it is non-positive. So once zero is included, that's where the idea of semi comes into it. Okay, so significance of semi-negative definiteness, right? This property is crucial in various fields such as optimization, stability analysis is coming into it again, control theory, where it helps to determine critical point stability conditions and system robustness. So semi-negative definiteness can actually be useful in such contexts. Okay, all right, so let's talk about indefiniteness, right? We've talked about something being positive definite, negative definite, and the semis in between. But then how about we talk about indefiniteness, right? So a matrix A is indefinite if it has both positive and negative eigenvalues. So if you have a mixture of positive and negative eigenvalues, then you say the matrix is indefinite. You cannot actually say it is this or that, right? For instance, okay, consider the matrix A, which is 1, 1, 1 minus 1. Its eigenvalues are lambda 1, which is root 2, and lambda 2, which is minus root 2. One is positive and one is negative. So because of that, this matrix is actually indefinite. And that can really be problematic, right? You don't know where to actually place it. For instance, if you're talking about stability analysis, right, and you get this, if you get one positive lambda eigenvalue and a negative eigenvalue, you cannot say anything about the stability of the system. In fact, you can say the stability is indeterminate, so to speak, because it is indefinite. You need both eigenvalues to be negative or all eigenvalues to be negative to say there's stability. But then, of course, you can still manage maybe one zero value and every other thing is negative. You can still manage that. But then if some are positive and some are negative, then you have all these issues going on. So probably you have a kind of chaotic situation right there. So the significance of indefiniteness, right? Indefinite matrices are arise in optimization problems with both positive and negative constraints. So, in optimization problems, sometimes you can have some constraints that are unrestricted, right? And you have some constraints that should be negative and some are positive. Maybe one day soon I'll get to talk about maybe do something on optimization. So they also play a significant role in analyzing quadratic forms and classifying critical points. Yeah, I hope to do a video or do some maybe one or two videos possibly on quadratic forms in the future, right? So look forward to that. So if you have not subscribed, you want to make sure you subscribe and hit the notification bell. So when such a video drops, you get to know about it. So in conclusion, right, understanding the definiteness of a matrix in terms of its eigenvalues is crucial in various mathematical applications, such as optimization, eigenvalue problems, differential equations. I mean, under this, you get to talk about something like dynamical systems, right? So that's what we talk. We are concerned about things like stability. We are concerned about things like chaos. You know, we are concerned about stability and chaos and all that. So definiteness is actually very useful. So as usual, I have some practice questions for you. So you can try your hands on this. Given the matrix A4132, determine whether A is positive definite, negative definite, semi-positive definite, or indefinite. Justify your answer using the eigenvalues of A. Then consider the matrix B minus 200, 240, 0, 0, 1. So classify, of course, this is a triangular matrix. Also, in fact, this is a diagonal matrix. And of course, you don't have to do anything to even know the eigenvalues. The eigenvalues are staring at you right there. So classify B as positive definite, negative definite, semi-positive definite, or indefinite based on its eigenvalues. Provide a brief explanation for your classification. So thank you for listening. See you in the next video.